Okay, hi guys. So I wanted to talk to you a little bit today about just simple differentiation. So what we've been looking at so far is when we're examining something by first principles. So say for example we have f of x equals x squared, and we can use our first principles formula with our limit. Sorry, I always forget the limit as h approaches 0. And we know from the examples that we've done that if we find our derivative by first principles of this function, that's going to equal 2x. Now, say we look at a few different functions. Say we take x cubed, and we're going to look at 4x squared, and we're going to look at negative 6 x to the power of 4. Now, say for example I'd done all my first principles of these functions and I'd come out with the following derivatives. Sorry, I thought that changed colours and it didn't. There we go. Why? Okay, so and we found that it came out with the following derivatives. We came out with f dash of x equals 3x squared. Okay, again pretending that I'd gone through the whole first principles process. I would end up with f dash of x equals 8x. And I'd end up with f dash of x equals negative 24 x to the power of 3. So from this we can come up with a general rule for finding derivatives of any function. We can say that our derivative of f of x is equal to, say f of x equals x to the power of n, then our derivative of that function is going to equal to nx to the power of n minus 1. So we bring down the power from our function, we bring that down to the front, and we just decrease that by 1. So if we look at this 4x squared, for example, we bring the 2 down to the front. We've already got a coefficient there, so we multiply it by 4 times the 2 gives us 8. And we decrease that power by 1. So 2 minus 1 gives us 1, and we have to remember there's a little imaginary 1 on that x there. If we look at this 6x to the power of 4, again, we bring that 4 down to the front. 6 times 4 gives us 24, so we've got negative 24, decrease that 4 by 1, that gives us x cubed. Excellent, there we go. So that's pretty much simple differentiation. Now, for some reason, textbooks always want you to differentiate separately, but say you have a polynomial that has more than one term. Say, for example, f of x equals x cubed minus 5x squared plus 6x minus 15, for example. Then we can find the derivative of that function by differentiating each part separately. Okay, so we take the derivative of each part individually. So we can look at this as 3x squared minus 10x plus 6 again. So we've brought that 3 down to the front, decreased it by 1, got us 2. Brought the 2 down to the front, multiplied it by 5 to get negative 10. X to the power of 1. 6, now that x is going to go from 1 down to a 0. Anything to the power of 0 is 1. So that x goes and we're left with 6. And the 15, that has no derivative on the 15. And I'm going to explain why to you. Okay, so I'm just going to show this to you. So hopefully what you can see here is you've got 4 different functions, and all of these have just got a varying vertical translation. So this first one here, that purple one, that's x squared plus 3. The one below it's x squared plus 2. The blue one there, that's x squared minus 4, and the red one, that's x squared minus 6. If you imagine that we drew like a vertical line going down through negative 1, graphic calculators aren't great at drawing vertical lines, so that's why I can't really put that in there too much. But if you just imagine that there's a vertical line through that negative 1 point, hopefully what you can kind of see, or actually, no, we've got the vertical line through 0, so let's look at that. So let's look at the vertical line through 0. Hopefully what you can see is that corresponds to like the same point on all the graphs. And it's not the same coordinate, but it's the same feature. So that's at all of our turning points. So what we can kind of deduce from that is that the gradient at all of those points are the same. Regardless of what that constant is or what the vertical translation is, that's always going to be the same gradient at that point there. And that's true for all of the points on this graph. Vertical translations have no effect on gradient. Only parts of functions that have variables affect the gradient. And again, we should kind of know that, because if we look at, say, a function which is, say, y equals 8, that's purely a constant, and we know that horizontal lines have a 0 gradient. So any horizontal, any just purely vertical or purely constant value we have has no gradient whatsoever. If we look back onto here, so this is where we're up to. Okay, so that 15, that just kind of gets cancelled out. That's not included in our derivative. So our derivative ends up being f dash of x equals 3x squared minus 10x plus 6. Another thing on notation, just in case you've forgotten from the other day, is that, say our function is y equals 3x squared minus 5x plus 4. That means that the derivative of that function would be dy on dx equals 6x minus 5. Right? Again, just noting that that notation is different. And say, for example, our question said something along the lines of differentiate the following. Something like that, where we're not given that, that's an expression. We're not given it with regards to any other variable, f of x or y, or whatever we're graphing with regards to, then we would, in this case, we would use the notation d on dx. Okay, and that's just referring to the fact that we're just looking at the change compared to the change in x. It's not the change in anything else. Okay, and that's going to give us 2x. Excellent, really good. All right, just a couple of harder examples. So I'll just insert a new page. Okay, so a couple of harder problems. For example, where we need to kind of simplify our expression before we can take our derivative. So say, for example, we had something like this. Say y equals square root x. Now, square root x isn't strictly a polynomial, but we can turn it into index form, which will allow us to use that rule that we had before in order to find our derivative. So we're just going to transform this function for y equals x to the power of a half. Then what we can do is we can take our derivative once it's in this form. What we're going to be left with is dy on dx, so our first derivative equals to, we can bring that half down to the front, 1/2 x to the power of negative a half. Now, extra kind of advantage on this, or extra extension, is we want to try and put it back into surd form, and that's because surds are much easier to look at than negative powers. So we still have our 1 that's on the top of the fraction. It's from that 1 from the half there. The 2, that still goes on the bottom, so we're dividing by 2. And then we're going to chuck in here, negative a half means we've got a square root, and it's on the denominator of our fraction, so square root x. Another function that we might want to look at, which might involve a little bit more simplification, is if we had something like 1 over x square root x. Now, for this one, we want to be using some index laws again before we differentiate. So we've got 1 over x to the power of 1, that's that x there, times by x to the power of a half. Now, this is positive a half because it's still on the bottom of the fraction. If we brought that up to the top, it would then become a negative a half, but when it's still on the bottom, it's positive a half. From there, we can use our first index law, which is the addition multiplication one, which we can then add those together, and we're going to get x to the power of 3 over 2, 1.5. We can then bring that x up to the top, and it then becomes a negative. From there, we can take our derivative. So we might say dy on dx equals negative 3 on 2, bringing that power down to the front, x, and then we want to decrease 1, so our power overall is going to be negative 3 on 2 minus 1, which is going to be x to the power of -5 on 2. And again, if you would like, this one's a bit harder to put back into fractional form, but we have -3 on the top. That comes from that. That comes from that -3 there. Oh, still going to do the blue over, so stick with blue. Over 2, that's on the bottom. And then here, x to the power of 5 on 2, that's like 2.5. So we're going to have x to the power of 2, and then x to the power of 1/2 is our square root x. All right, another couple of ones just really quickly. Okay, say we had, these ones generally people don't find too hard. So say for example you had, x plus 2, x minus 3. I think most people are familiar now that you would have to expand that first. That I think in A-level maths, that should seem fairly self-explanatory to us. So our derivative is going to be 2x minus 1. What's more complicated is where we probably need to factorize. Factorizing seems, for some reason, a little less counterintuitive than expanding. So say, for example, we had the opposite of that. We had x squared minus x minus 6, and then we had that all over, say, x plus 2. Now, a lot of people wouldn't look at that and necessarily know what to do, but we do need to factorize our numerator. We're going to have x plus 2, x minus 3, all over x plus 2. We can then cancel that out. And what we're going to be left with is dy on dx equals x minus 3. That x has got a 1, that comes down, that just becomes 1, and then the minus 3 goes to 0. Just remember that if you are looking at something like this, you might want to potentially try and use a calculator to help you. And you could sorry, that was just just someone at the door. So anyway, like I was saying, if you had a function like this, you could use a graphics calculator to check. So even if your calculator isn't as sophisticated as this one, you should still have a derivative function. And I know on the Casios, it's up on the top right hand side. So somewhere up there, you should have a button that looks, and it should, when you press it, it should come up like that. You might have to go shift first. But you should come up with like a preset equation like that. Now, on this calculator, I'm going to type in d on dx, and then I'm going to type in that equation that we had before. So it was x squared minus x minus 6. Okay, and then on the bottom we had x. What was it? It was an x plus 3, x minus 3, or x. Yeah, we had x plus 2. All right, so if we look at that and then we take in x plus 2, then if we're looking at our derivative, we can say put in a value of x. So say we choose 5. Now, this function won't differentiate for us, but it will tell us what the value of our derivative should be. So if we then work that out, we can see we get 1 as an answer. We know that our derivative is equal to 1, so that should tell us that we're on the right track and we've done the right thing. If we had a more complicated one like this one here, when we were taking the derivative x squared minus x minus 6 without the fraction, then if we looked here, we want x squared minus x minus 6. If we looked at our derivative when x equals 4, when x equals 4, we get a derivative of 7. If we know that our derivative formula that we found was 2x minus 1. So if we now substitute in 2 times 4 minus 1, what we should get is the same value. And if we get the same answer for both our derivative that we found by hand and the calculated derivative at that same point, then we know we should be on the right track. Okay, that's it for me for today. Hopefully this helps again.